So the third part of the first lecture, we'll start looking at sampling. Look at sample size and randomisations, talk about the various national bodies who do sample analysis. We'll look at the process and sampling plans, talk about the importance of British standards, and again reiterate sampling and separations and extractions, and there's a couple of team exercises for you to do as well. Okay, so sampling, the little gummy thing that we've got here is probably not representative of the entire population. They're all many different colours, for example, though it's probably the colours the only thing that's probably different. The question becomes, in many cases, how do we get a sample that is representative of a bigger population? So here's a cake. You've been asked to do a chemical analysis of the composition of the cake. You've been told that you only take a small amount of the cake for analysis. How would you make sure the sample you analyse is representative of the whole cake? Quite a difficult problem. So doing a sort of qualitative analysis, if you will. It contains strawberries, so it's got cream, it's got green stuff, which people have suggested to me might be the strawberry leaves. It's got chocolate, it's got icing. So lots of things, there's 5 different things there, but that's only the outside of the cake. Who knows what's happening on the inside? It could be very heterogeneous indeed, to use the phrase that will be used a few times. How do you get a representative sample of this? There are techniques which we'll discuss later on when we're talking about the labs. Now, one thing we could do is, if this company's made 10,000 cakes, we could take all of them. The company will probably object to that because they would have none to sell. But then if we took one, sample size n equals 1, probably not very good. You're almost certainly going to need more than one sample. N equals 1 isn't really a representative sample size. It's more of an anecdote. But we certainly can't take all of them. Okay, so going from the top where we've got one cake, not particularly representative. As we increase the number of cakes which we can use for sampling, the results we're going to get do become more representative. Basically what we do is we'd have a strategy for analysing a sample or samples from each cake, and then we'd collate the results together, do averages, and that would probably give us a good idea of what's happening in the whole 10,000 cake batch, whereas one probably wouldn't. Randomisation may help. So this is a schematic of the working day, starting on the left where people have just turned in at just before 8:30 to quit in time, perhaps 4:30. Now the cakes made at the beginning may not be exactly identical to the cakes made at the end. People are fresh, they haven't been working all day, they may be different. So what you would probably do is find some method of randomisation and say we'll pick out a cake made at 10 o'clock, a cake made at 2 o'clock, a cake made at 3:30. Something like that, something which will allow you to get a random sample. Okay, so here's some Food Standards Agency's videos on sampling. I'm not going to open them up, you can link them yourselves. There are also a set of tutorial questions and tutorial exercises associated with these, which you can find in Blackboard and associated with the SWAY that holds all of this documentation together. The LGC, what used to be known as the Laboratory of a Government Chemist, is where this stuff is done nationally. If you click on the link, it'll open up their web page. It recruits chemists to it rather than food scientists, and they do quite a lot of stuff. There's a fact sheet about what they do there. So they do lots of things. Like Science for a Safer World is their core purpose. They do analysis. They do genomic analysis. They serve all sorts of people, including the food industry. And there's a list of the various things that they do. So worth having a look at if you're interested. Okay, so a typical sampling process. Here's some cheese, they're making cheese. Again, we can't grab the whole thing. So we're going to take a sample and we collect the sample. What we'll probably do is break it up into smaller parts. Now, if you've watched the FSA video, you'll see this is what they do. They often break samples up into 3 parts. Leave one with the person who they've taken the sample from, and then they use 2 one for a reference sample and 1 for analysis. They will find a way of storing it so it's stabilised. In this case, it's a cheese, so a cool box will probably do. Cheese has a reasonably long shelf life, so that's probably going to be okay, provided you keep it under the sort of conditions which you would keep food under domestically. Then you probably need to do some sample preparation, and more of this in a little bit later on in this lecture. Often we need to separate the things that we're interested in from what we call the food matrix. So if we're interested, for example, in beta-carotene in peppers, we need to separate the beta-carotene from the food matrix, which is the pepper as a whole. We may also have to do some chemical reactions to make it visible to things we want, the systems we want to use to do it, and then finally we'll do the analysis. So it can be quite a complicated process. It's by no means a trivial process. Okay, so developing a sampling plan. This sort of covers off overall our ambitions, I guess. The one at the bottom is probably the most important. The laboratory sample must be representative of the population. There are statistical methods which we can do which will help us this, which again we'll talk about later, probably in the lecture series. But there's a couple of definitions here. The population, so that's all the cakes manufactured perhaps on a particular day. The sample is a fraction of cakes we've taken by the methods we described earlier. And then we're going to use some of them for analysis. So as discussed again, FSA inspector might take 3, but we'll only use 1 for direct analysis. And then that'll probably be broken up into 3 parts. Whenever you do a chemical analysis, you normally do it in what's said to be triplicate. That is, you repeat the experiment 3 times. They may have subsamples from different stages of the process. It's probably not relevant for a cake, but there may be some foods where that is relevant. And as I mentioned right at the start, the overall thing is it must be representative of the population. The holy grail, the great source of these things, is the British Standard Methods online, which you have access to. You get it via the library. I'm not going to log into this, but if you go to the library and search in the databases for British Standards, and then search for food methods, you'll find a wide range of different food methods given in considerable detail. So here's an example which I would suggest you find. Milk products guidance for sampling. So this covers the sampling report, which includes the personnel who will be doing the sampling, how samples will be sealed in labels, what is the nature of replicate samples, and the format of the report itself. So I've got a little exercise coming up here for you to do. Individually locate this British standard using library databases. In small groups, in Word, draft up a sampling report based on the British Standard recommendations and post to the Teams group. And then we'll analyse it in our usual way for these sorts of things. We'll do a sort of team analysis based on 2 thumbs up and a wish, 2 things we really like about it, and 1 thing we think would make it even better. We should also think about, is a Microsoft Word file the best way to store this information, and what are the tools you might be able to use. Bear in mind you may need to sort of find this information in the future. Typically you have to keep this information for at least 5 years in the food industry, and sometimes longer. Okay, just to go back to something we touched on a little bit earlier on, the complication of food analysis. Again, just reiterating what we said earlier on about quantitative and qualitative analysis, and bringing in another definition, analyse. A substance whose chemical constituents have been identified and measured. So that might be beta-carotene, might be vitamin C, might be the amount of fat, might be the amount of water. And if you're looking at water in a particular food, water would be the analyse. Here's our orange again. There are many things we might analyse. If we want to know how much water it contains, we could weigh the orange, cut it into small pieces, heat it up to drive the water off and weigh what's left. That's how many estimations are done, but there are other better methods such as using the equipment there, which is what's called the Dean and Stark apparatus. Now it doesn't look particularly sort of accurate, and you may be thinking, and you'd be right, it isn't. It's not the most fantastically accurate method, but it's a routine analysis method used in a wide range of food situations. These days it will probably be done automatically. Most of the routine methods we do these days could be done automatically. We just put the samples in a machine. It'll probably do quite a few of them simultaneously. Okay, moving on. Yeah, so one thing is this substance, ascorbic acid, vitamin C. There's only a small amount as we saw in orange. People who lack vitamin C may develop a condition called scurvy, which we've again discussed in the past. Now, one thing about vitamin C or ascorbic acid is that it is water soluble, which makes life quite simple. We need to extract it still. We often analyse it using the method I've mentioned a few times, high performance liquid chromatography. The action's quite easy. We just use a food blender to produce orange juice. We have to be careful not to heat the sample up because the ascorbic acid is damaged by heat. Then we pipette the known volume of our orange juice sample into a volumetric flask made up to a known amount. We normally filter it, which is what the person wearing the gloves there is doing, and then we can do HPLC analysis based on standards in a similar way we did last year. So vitamin C is quite straightforward. Beta-carotene is a bit more complicated because beta-carotene is not water soluble, it is a hydrocarbon. So in this case we'd take our pepper, we'd slice it up, we'd homogenize it in the blender, again being careful to make sure we don't heat it up. Another complication here is that beta-carotene is damaged by light. So when you do this experiment, you wrap all your equipment up in tin foil to make sure you don't cause damage. But okay, to go back to where we were, we've homogenized it. Then we do what's called an extraction with methanol. Now beta-carotene is soluble in methanol. We filter off the stuff we're not interested in. Then we use a piece of equipment called a rotary evaporator, and I will link to some resources on what a rotary evaporator is and how it works a bit later on. And drive off the solvent. Then we add a known volume of solvent, make it up to a known volume, and then we can again do HPLC analysis. So again, a little bit more complicated. Although these things are done routinely, when you're doing a new analysis, perhaps with a student project, you'll find out that most of what you're doing is trying to get the method to work consistently. What's called method development and validation. Okay, so here's a team exercise. We mentioned the crab poster before. So have a review of it as a team and draft a sampling plan for heavy metals in crab. Where would you get your samples from? Let's see, crabs. How many would you need? How would you transport and store them? What consideration would you give of issues such as crab anatomy and gender? I'll tell you straight away, the analysis you'll have to do a bit of reading on is microwave digestion followed by ICP-MS analysis, which we will look at into a bit later on. But you might want to do a little bit of reading on that now. Okay, right, there we are. That's the end of part 3. I will be back in a moment.